Streamline flow is nothing but the path taken by the fluid particle under steady flow. The only difference here is that since here the water is exerting a pressure, it will be P1 pressure here and P2 pressure here. When it is passing through the first opening, let's say that it is having a velocity of V1. So according to conservation of mass, we are going to express this conservation of mass in terms of density and volume. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we are going to deal with some mechanical properties of fluids. So till now we were seeing and studying about fluids that is in rest. Now we are going to study about fluids that are in motion. So what exactly is streamline flow? So you already know that streamline flow means when a liquid is flowing without any breaks, that is without any backflows, you can see a path traced out by that particular liquid in steady flow. So we can say that streamline flow is nothing but when a fluid particle is exhibiting steady flow. The path taken by a fluid particle in the state of a steady flow is known as streamline flow. So what exactly is a steady flow? Steady flow again can be described as if I take a particular point here. If I take a particular point here and if I measure the velocity of the fluid particle in that particular point, then I can say that, okay, if that particular velocity of that fluid particle in a given point does not change, then we can say that, okay, then that particular fluid particle is exhibiting steady flow. So again, just to put it in words, we can say that streamline flow is nothing but the path taken by the fluid particle under steady flow. And steady flow is nothing but it is the if at any given point the velocity of the fluid particle remains constant in time, then we can say that, okay, that has steady flow. Basically, if you want to picture it, you can imagine it as if you have a water balloon like this. If you have a water balloon like this, if you poke a hole in it, if the pressure is enough, you can see the water squirting out like in a particular shape. So it will be like that. It is standing still, so perfectly flowing out that you cannot actually see if the water is flowing or the water is standing still. That particular path taken is known as streamline flow. The path taken by that particular fluid particle is known as streamline flow. And the nature of that particular flow, that is each fluid particle in that particular given position is not changing its velocity. It's not like here it is 10 meter and suddenly it's 25 meters. No, right? It is constantly having a definite set of motion. So we can say that if that is the case, then there is steady flow. If there is steady flow, then we can say that there is streamline flow. And what happens if streamline flow is obstructed? That is, instead of fluids going like this harmoniously, instead of that, suddenly the fluid backflows or there is chaotic flow occurring. Then what will happen? Then we can say that, so this particular flow which obstructs streamline flow is known as turbulent flow. So this is known as turbulent flow. You might have seen rivers which are flowing neatly, like in one particular direction, rivers will be flowing so neatly. That is steady flow. That is, rivers are flowing so steadily in streamline flow. But if there is a rocky river in which the water is hitting here, hitting there and coming back and forming bubbles and all that, then we can say that when the water meets that particular object, there is backflow of water. I'm taking water as an example, the river as an example. So when the streamline flow is obstructed and the pattern is changed, the streamline nature is obstructed and now it is curving and whirling around, then we can say that, okay, there is turbulent flow in that particular motion. So that is turbulent flow and streamline flow, and for the streamline flow we actually need steady flow. Now, equation of continuity. This is very important. This and Bernoulli's principle is the most important thing in this particular chapter. But again, what exactly is equation of continuity? You might have used many hoses in your life, right? You might have used it to spray in your gardens, you might have used it to wash your car, wash your bike, even maybe wash yourself. So you might have seen that when you're holding a hose like this, the water pressure will be not enough. So if you want to reach somewhere a little bit further away, you just hold your tip of your finger to the hose so that the water just squirts out a little longer. So why does this happen? It is actually because of a simple principle hidden in the physical world. So we are going to learn about that particular condition. That is, why does water squirt out when we decrease the area of a hose? Because the water coming from the pipe is not changing. The only thing we are changing is the opening. That is the area under which this water is coming out. So when we change that particular area, the speed of the water is suddenly changing. The velocity is changing. And if we increase the area, then suddenly the velocity is decreasing. So why does this spooky phenomena happen? So that is what we are going to study in this particular session, that is equation of continuity. So again, I have a slightly exaggerated opening here. That is one bigger end and one smaller end of a same pipe. Let's say one pipe is coming like this and suddenly it increased in area. So I can say that, okay, this side, this opening, let's say it has an area of A1. It is having an area of A1 and the other end is having an area of A2. Okay. Now imagine that some kind of fluid is passing through this particular pipe. Oh, let's imagine it to be water or a liquid, any type of fluid that is flowing through this particular pipe. Then initially when it is passing through the first opening, let's say that it is having a velocity of V1, and when it is obviously passing through the second point, it will change its velocity, right? So when it is passing through this particular point, it is having a velocity of V2. That much is true, right? So when it is passing through area 1, it will have a velocity of V1. When it is passing through the smaller opening, it will have a velocity of V2. So the only one condition I am taking here is that the opening A and opening B, the two openings I am calling it as A and B. So the only condition I am taking here is that if this is A and if I take some random point here and call it as A dash, and here also I am taking one random point and calling it as B dash. Okay, so I am taking two random points. So from A to A dash the liquid will be flowing, and from B dash to B also the liquid will be flowing. So the only consideration I am taking here is that the time taken for this particular liquid to reach from A to A dash and B dash to B or B to B dash is in delta T. That is, in delta T time, the water will reach from A to A dash. So obviously, if water is flowing through here and at some random moment I'm taking, okay, I'm going to measure how much water is reaching from A to A dash or what time it is reaching. Then obviously, some water is being pushed through this particular opening. So when it is pushed through, it reaches in delta T time. When this much water is pushed, then obviously here also the same amount of water is being pushed out, right? Because if let's say 1 kilogram of water is being pushed in here, then the same amount of water which was stored here is being pushed out through this small opening, right? So which means that the same amount of water is passing through this particular opening. So the same amount of water reaches from A to A dash and B to B dash in delta T time. So the time taken for the water to reach A to A dash is equal to B to B dash, which is equal to delta T, which means it just happens in the same time. Now, I know that this much water is being displaced, but I don't know through what distance. I don't know this distance and I don't know this distance because again, I took some random points A and A dash, B and B dash. So how can you define that particular distance? We can actually define it in terms of the variance we know. That is, we know what is the velocity. We know what is the time taken. So using velocity and time, how can you define distance? It's very simple because distance by time is velocity, which means velocity into time is equal to distance. So we can just say that, okay, here it is delta t. So V delta t will signify the distance, or simply we can say here that it will be V1 delta T here, because the velocity of area 1 is V1. So that is why here it is V1 delta T, and here it is going to be V2 delta T. Now, how much water is being displaced? That again is also very simple. Since this is a closed container, if m amount of water is here initially stored, and if I push in some more water, this m amount of water won't disappear, right? That m amount of water will be pushed through this particular small opening, which means mass is not lost. Simply, we can say that according to conservation of mass, we can say that how much ever water is being stored here, that much is being pushed out, right? So again, in this particular chapter, whenever we say in terms of mass, we'll actually take density. We generally express fluids in terms of density. So we already know that mass by volume is equal to density, which is rho. So which means that rho V is equal to mass. Right. So according to conservation of mass, we are going to express this conservation of mass in terms of density and volume. So rho times V is actually mathematically equal to the mass. So we can say that, okay, rho V will be substituted here. So again, according to law of conservation of mass, we can actually say that how much ever mass is traveling from MAA dash, that is how much ever mass is being pushed through this distance, the same amount of mass will be pushed from this distance also. So this will be equal to MB dash B, right? So again, expressing mass in terms of density and volume, we can say that, okay, rho V, here density of the liquid won't change. So again, the only thing changing here is volume. This is velocity, but this entire volume is different. So let's say from A to A dash volume and B to B dash volume is different. So we can actually see that, okay, from A to A dash is equal to rho V B dash to B, right? The only thing changing is the volume, because density of the liquid remains the same. It's not like suddenly here it is one liquid and suddenly there it is another liquid. It is the same liquid. So the volume is the only factor that is changing. Let's put it as equation number 1. Now again, the common factor in this particular equation is the density and the density. So from this we get that, okay, volume that is being displaced through this distance is actually equal to volume that is displaced through this distance, which means the volumes are equal. Now again, we have to express volumes in terms of the variance we already know, that is in terms of area and this particular displacement. So again, if you look at this particular angle, you can see that, okay, if I tilt it, it is nothing but a cylinder, right? The volume of this particular area or that particular area is nothing but the volume of a cylinder. So what is the volume of a cylinder? So if you don't know, you can note it down. The volume of a cylinder is actually expressed as this particular base area. So base area into height. So base area times height will give you the volume of a cylinder. So again, this particular volume now can be expressed as base area into height. So again, what is the base area? The base area is nothing but this area, that is A1. So here it will be A1, and base area into height. Height is nothing but this particular distance, and we already know that, that is V1 delta T. V1 delta T. So that will be equal to, again, for the next cylinder also. There the area is A2. The distance is V2 delta T, right? So A1 V1 delta T is equal to A2 V2 delta T. Delta T and delta T cancels out. So we can write that A1 V1 is equal to A2 V2, or simply this means that, this implies that A times V is equal to a constant. A times V is equal to a constant. That is equation of continuity. It just states that if area increases, then velocity should decrease. And if area decreases, then velocity should increase. So that is why when you use a hose to water something and you suddenly press and hold at the end of the hose, the water squirts out faster because the area is now reduced, which means the water that is being pushed through must come out, which means the velocity must increase. So that is what this equation states, and it is known as equation of continuity. Now, the next thing is Bernoulli's principle. This is paramount of importance. This contains paramount of importance because this is the most important bit of information you need in this particular chapter. And this is slightly a longer derivation, but it is very important. Bernoulli's principle actually helps us even to achieve flight. So again, this is very important. So again, in this case also, I'm going to take a pipe which has two openings. The only difference is that there is now a difference in height factor also. There, the height factor was the same. Here, the height factor is actually different. So now, let's say that fluid is flowing from A to B and the opening sizes is also different, which means here the area will be, let's say, A1. That is this area, let it be A1. And this area, let it be A2. And again, the velocity of this particular area will be, let it be V1, and here let it be V2. And again, we are considering one more area here. Let's call it as A dash, and one more area here. Let's call it as B dash. So again, liquid is flowing. So when liquid is flowing through here, it obviously pushes the other liquid to the other side. So obviously, it is going to be pushed out. Now, the only difference is that this particular pipe is somewhat raised from the ground. So that, let's say that this will be having a height of h1 and this will be kept at a height of h2. So the height is different, the area is different, the velocity through which the water is being transported is also different. So everything is different, but the things we apply remains the same from the equation of continuity. That is, here the distance again we found out from the last equation. It is going to be V1 delta T, and here it is going to be V2 delta T, right? From the previous equation, the same thing. And now the only difference here is that since here the water is exerting a pressure, it will be P1 pressure here and P2 pressure here. So the obvious doubt from the previous session will be that, so you told that water will be exerting the same pressure. That is true. According to Pascal's law, fluid will be exerting same pressure only if it is in rest, static fluids. Now in this particular case, the water is actually flowing. So Pascal's law does not apply to fluids in motion or dynamic fluids. It only applies to fluids in rest. So again, in this particular case, the pressure exerted by the liquid or the fluid in this particular region and in this particular region will be different. For example, if water is flowing in this particular direction, the pressure exerted will be in this particular direction. It is trying to push it through, right? But in this particular opening, what happens is that the pressure is being directed in the opposite direction, right? So here it is trying to push the water back in. Here it is trying to push the water forward. So here pressure will be in this direction. Here the pressure will be exerted in this particular direction. So direction of pressure will only be different. Now, how can you solve or how can you derive this particular equation? So again, we are only focusing this from an examination standpoint of view. In the class, I'll explain it clearly and neatly. What is the relevance of this particular equation? What is the relevance of this particular derivation and all that? But for now, we are only focusing it from an examination standpoint of view. And again, we can say that we are going to start this equation. Since the fluid is in motion, we are going to start the equation using kinetic energy, or simply we are going to start by taking the difference in kinetic energy. That is, the fluid which is having a small amount of fluid. We are taking only small amount of fluid. So the fluid that is having a small amount of mass, let's say delta M, that small amount of mass is passing through here, which means it is in motion. So I'm going to take what is the kinetic energy here and what is the kinetic energy here. Or simply I'm going to take the change in kinetic energy. And also, since it is kept at a particular height, I'm also going to take what is the change in potential energy. So again, I'm going to take the kinetic energy difference and potential energy difference and compare them. So first I'm going to start with what is the change in kinetic energy. So change in kinetic energy, or simply del Ke, is given by Kf minus Ki. Right? Kinetic energy, final value minus kinetic energy of the initial value. Then I can say that, okay, the equation for kinetic energy is nothing but half mv square, but again here it is only a small amount of liquid, very small amount of liquid that is passing through. So I'm taking it as delta m, the small amount of mass that is passing through, delta m v what? It is final. So here it will be v2. So v2 square minus half delta m v1 square. Right. So again, this particular delta m should be expressed in terms of density. So we already know that delta m divided by delta v is equal to rho. Right. Small amount of mass passing through a small volume is known as density. So again, delta m will be equal to rho delta v. So instead of delta m, I'm going to write half rho delta v, where delta v is the volume, the small amount of volume, times v2 square, where v2 is the velocity at the final velocity, minus half again rho delta v v1 square. So let's put it as equation number 1. Delta Ke, that is the change in kinetic energy, is actually equal to half rho delta V times V2 square minus half rho delta V times V1 square. I know rho and delta V is common, but don't take it outside right now. We have further use for it in the coming steps. So I'm going to keep it as it is and call it as equation number 1. Now, similarly, I'm going to take the change in potential energy. Change in potential energy again will be equal to final value minus initial value. Final value is mgh. So again, here it is delta m, small amount of mass, m, and g is the acceleration due to gravity, which is seen everywhere in Earth or any planet you are performing the experiment in. So we can say that it is going to be delta m g, and it is going to be h2, delta mgh2. So mgh final minus initial, delta m g h1. Right. Again, now instead of delta m, we are going to substitute rho delta v. So by substituting, we will get rho delta v gh2 minus rho delta v gh1. So this is equation number 2. Now the last thing we are going to calculate is known as work pressure. So what exactly is work pressure? Work pressure is something you will actually learn in the coming chapter, that is in the thermodynamics section. But right now we also need work pressure here. So simply we can say that it is nothing but the work done by the pressure in order to push or pull this particular liquid. So here I told you the pressure is doing a work in order to push this particular water through this particular pipe. So that particular work done is being calculated here. So we are going to calculate the kinetic energy, the change in kinetic energy, change in potential energy, and the work pressure, or simply the work done by the pressure in order to push this particular water. So again, here the net work done is actually equal to WP1, that is work done by the pressure at the smaller end plus work done by the pressure at the higher end, right? So there are two pressures doing two works. So the net work will be equal to the summation of both of those pressures combined. So again, the work pressure is actually given by the equation. Work pressure is given by the equation P delta V. Again, you will learn this in your thermodynamics chapter, but we need it right now. So we are going to discuss this here also. Just remember the equation. So then we can say that, okay, here this equation will become P1 delta V plus P2 delta V will be equal to the net work done. And one more thing is now there, last one step, and the equation is solved. Last one step, that is this work done will be equal to summation over change in potential energy plus change in kinetic energy. So according to the conservation of energy principle, we can say that the work done will be equal to the summation over change in kinetic energy plus change in potential energy. So again, W will be equal to delta U plus delta K. This is nothing but an expression of conservation of energy. So they can also ask this one. So what is Bernoulli's theorem related to, or what is equation of continuity related to? Equation of continuity is nothing but conservation of mass, because the mass is conserved there. Nothing is being expelled or suddenly vanishing there. So the mass is being pushed through. Here it is the energy factor that is being conserved through this particular equation. So Bernoulli's principle is an example for conservation of energy, and the application of equation of continuity is nothing but conservation of mass. So again, in this particular equation, we are going to substitute these values, which means P1 delta V plus P2 delta V is equal to delta U, which is nothing but rho delta V G H2 minus rho delta V G H1 initial minus final plus again kinetic energy, that is half rho delta V V2 square minus half rho delta V V1 square, right? So we have the equation right here. Now you can cancel whatever you want. So delta V is common everywhere. So you can actually take it out and cancel it out, or dividing throughout by delta V, you will get the delta V term being eliminated. So this term will be eliminated from all the parts, right? And now you can also see that there is 1, 2. So I'm taking all the ones to one side and all the second terms to one side. Then I can actually write it as P1 plus rho V1 square divided by 2, or that is half rho V1 square plus rho GH1, that is all the one terms together, will be equal to, if this goes to the other side, it will be minus. But the thing we have to remember here is that this particular work done is by the pressure, and in the previous case this particular work done is by the pressure, and in the previous case I already told you that the pressure is being applied in the opposite direction, which means that the work done, or simply the force, is being applied in the opposite direction, which means that the work done by the pressure there will be negative, because the direction is in the opposite side. So instead of P2 being positive here, P2 will actually be negative here. So P1 delta V minus P2 delta V will be the final form of this particular equation, because even though it is a summation symbol, P2 is actually doing negative work. So since P2 is doing a negative work, here in the final equation, when we take P2 to the other side, this is actually minus P2 into delta V. So when we take P2 to the other side, it will be positive. So when we take P2 to the other side, it will be positive. So P2 plus again rho V2 square by 2 plus rho GH2. So again, you have an equation in terms of ones and in terms of two. So this equation actually dictates that, okay, sum of pressure. So again, this half rho V1 square, If it was half mv square, we can call it as kinetic energy. But instead of kinetic energy, it is being expressed in terms of density. So we can actually say that this is the kinetic energy per unit volume. And similarly, this is the potential energy per unit volume, since it is being expressed in terms of densities. So the sum of pressure, kinetic energy per unit volume and potential energy per unit volume is actually a constant, because if I take everything to the left hand side, the difference will actually be equal to 0. That is similar to A1 V1 is equal to A2 V2, or simply AV is equal to constant. Right. In this particular equation, A1 V1 is equal to A2 V2. That means AV is equal to constant. Right. Similarly, here also P1 rho V1 rho G H1 is equal to P2 rho V2 and rho G H2, which means in general we can actually state that P plus rho V by 2, rho V square by 2 plus rho GH is equal to a constant. So this is Bernoulli's theorem, and this is the small derivation of Bernoulli's theorem. It just states that the sum of pressure and kinetic energy per unit volume and potential energy per unit volume is actually equal to a constant, and that is the definition of Bernoulli's principle. And it also can be used to prove that energy is conserved. It is also an example for energy conservation principle. So that is all about moving fluids in this particular session. Bernoulli's and equation of continuity is very important. Bernoulli's theorem and equation of continuity is very important. And we can just define Bernoulli's theorem as, if we move along a streamlined flow, if we take the sum of the kinetic energy per unit volume, the pressure and the potential energy per unit volume, it will be equal to a constant. And this is an example for conservation of energy. So I hope you have understood everything about Bernoulli's theorem and equation of continuity, how to derive that particular equations in this particular session. I'll see you all very soon with the remaining portion of this particular chapter. Until then, thank you.